Hello, everybody. First of all, a big thank you to the organizers for their invitation to give a talk here at Trends in Magnetism 2021. I will talk about microwave signal generation and neuromorphic computing using large spin Hall nano-oscillator arrays. And this is work by Sajid in his PhD thesis at the top left. Theoretical work by Roman Kimin, who now is a permanent researcher at the University of Gothenburg. Part of the work was done by Hamid Mazrati early on. Brilliant light scattering microscopy was done by our expert Ahmad Awad and the graduate student Shreyas Muralidhar. Some of the work towards the end was done by Himanshu Fulara, in particular the voltage-controlled devices. Micromagnetic simulations by Mikola Dvornik, and a lot of fabrication and measurements and support by Afshin Hushang. I also want to gratefully acknowledge our collaboration with Tohoku University. Shunsuke Fukami, Shun Kanai, and Hideo Ono have provided us with some stacks and a lot of insight and good collaborations. So the outline of my talk is I will briefly describe spin Hall nano-oscillators. I will describe the mutual synchronization in chains of such oscillators. And then I will spend more time on the two-dimensional arrays made from such oscillators and the mutual synchronization we can see in those. I will show that we can do the same type of neuromorphic computing that was done earlier by Julie Gourliet's group using spin-torque nano-oscillators. And then I will move on to the most recent results, which are voltage-controlled spin Hall nano-oscillators, which we think are crucial for moving these neuromorphic computing schemes forward. And some unpublished data towards the end where I'll show that we can control mutual synchronization of spin Hall nano-oscillated chains by the voltage alone. But very briefly, we will use platinum or tungsten to generate a spin current through the spin Hall effect, and by pushing a charge current through these layers, the spin Hall effect will create a transverse pure spin current, which we can then inject into a ferromagnetic layer. So there, in that layer, it can create damping or anti-damping. We will obviously use anti-damping because if we can manage to completely cancel the damping in a region of our device, we will get auto-oscillations of the local magnetization. And that's the very basis for the microwave signal generator. And to achieve that, there has been a number of different designs of spin Hall nano-oscillators. And for example, the first ones were nanopillars of MTJs, where the Cornell group showed that you could get slight oscillations of the free layer in the pillar if you passed a current through a tantalum underlayer. More dedicated work towards spin Hall nano-oscillators were pioneered by Demidov, Urashtin, and Demokritov, and here is their nanogap work from 2012 and the nanoconstriction work from 2014. And the variation of the nanoconstriction is the nanowire, which has been worked mostly on by Ilya Krivorotov, but also by other groups, I think, for example, Helmut Schultheis and others. We will, however, focus on the nanoconstriction because it is a particularly useful device for what we will work on and demonstrate in this talk. It has a very easy nanofabrication process. You need a bilayer and then you need to process a nanoconstriction in it. It has a very flexible device geometry. You can change the width, you can change the angle of that opening in the constriction, and you can change the materials over a very wide range. And the beauty of this design is also that you have direct optical access to the dynamical region. And not only that, you can put stuff on that magnetodynamical region, such as a voltage gate, which I will show towards the end of the talk how useful that can be. The nanoconstriction, as I said before, was pioneered by Demidov, Urashtin, and Demokritov, and they showed that in an in-plane field you can get a frequency generated by the spin Hall effect, and that frequency is well below the ferromagnetic resonance of the magnetic layer, which tells you that this is a localized mode. And they show that the mode was definitely localized to constriction, and they show that they can tune the mode by the applied field and the current. And we wanted to use this constriction for its simplicity, but we wanted to try to get propagating or at least extended modes because we wanted to synchronize many of these oscillators for various purposes. So what we started out doing was looking at what happens to this strongly edged localized mode if we push, or rather if we pull the magnetization of the free layer out of plane. And we do that by applying a magnetic field with an out-of-plane angle, almost 90 degrees, and relatively strong. So in this case, it's nickel iron, the material. So to get any effect, to get any angle of the nickel iron out of plane, you need to apply roughly a large fraction of the saturation magnetization, which is about 1 Tesla. So what you see here in the simulated work by Mikola Dvornik is that if you are at 70 degrees out of plane angle and 0.6 Tesla, you more or less have the same edge-like modes as you have in the in-plane case. But if you move towards the bottom right of this matrix, which is where you definitely pull the magnetization out of plane, you will get a different type of mode. And this is a consequence of the sharp spin wave wells at the edges, that they transform into a much more shallow spin wave well in the center. So once so the resonance of the system will now be primarily inside the constriction, and as we will see, if we pick one of these cases, 80 degrees and 0.8 Tesla, we pick this particular condition and we then drive a strong current through this device. That mode continues to expand and continues first to move inwards into the constriction, and then outwards out of the constriction as we increase the current. And this two types of behaviors will lead to a non-monotonous frequency dependence as a function of current. So you can see here at the bottom here, you can see how the frequency first decreases with current, and then has a minimum, and then increases with current. And this is a function of the mode center detaching from the edge, moving into the center, expanding outside of the constriction, and we're hoping that this should be then beneficial for synchronization. First, we confirm experimentally that this indeed happens. So we made platinum nickel iron bilayers, and we put them in an out-of-plane field, and we saw indeed that we get this telltale sign, a non-monotonic frequency dependence, which is consistent with mode detachment and expansion. And also the power increases strongly as the mode expands into the center. We can now test, and the first test will be if we make 2 such constrictions and see if we can make them to synchronize. And that is indeed what happens. First, at lower currents, we see 2 individual signals. We can see that they are both redshifting. That is, when we increase the current, the frequency goes down. So that's the sign of an edge mode that has a negative nonlinearity. And we can also see that they're doing this alone. They are not affecting each other. If anything, their line width is improving. As we drive stronger current, we have a stronger, higher amplitude of the signal, and it's a better defined signal, basically. But then as the first oscillator starts to turn around, which means that it will now expand into the constriction, we can see that slowly its line width is deteriorating, and it's also deteriorating the other oscillator. And we can see that the other oscillator never really turns around. Instead, it's pulled towards the first one. So there's frequency pulling, which is a sign of intermittent phase locking. The line width deteriorates. We can barely see a well-defined signal here until the 2 oscillators decide to give up on this, detrimental behavior, and instead agree on a single frequency. So they now will oscillate on a single joint frequency, which is more or less the average of the 2 original frequencies. And once that happens, we have a much stronger mode volume now for that single mode. The power goes up tremendously, and the signal coherence also goes up tremendously. And after that point, these oscillators stay synchronized for all currents. We looked at longer chains in this first work, and we could find mutual synchronization up to 9 oscillators we tried. And here you can see to the left is the SEM image. The black are the nanoconstrictions, and to the right you can see the electrical behavior. More and more signals combine into a stronger and stronger signal. The signal we got was about 50 times larger than a single oscillator. And theoretically, if all was identical, we should get an 81 times larger signal, because we're synchronizing 9 oscillators, and 9 squared is 81. We can look at this chain now with Brownian light scattering microscopy, and we see that all the oscillators are energized. And if we look at the frequency distribution, we can see that the frequency is the same throughout the array. So this is a fully synchronized 9-oscillator chain. And we're currently looking at longer chains, and we believe we have mutually synchronized 21 of those, for example. But what I want to talk about today are two-dimensional arrays. And this was a large part of Mohammad Saidinejad's thesis. So he decided to make 4 different types of constrictions, 50 to 100 nanometers, 120 nanometers, and their separation P for pitch, he changed from 100 nanometers to 300 nanometers. And as we will see, these differences have large impacts on the synchronization behavior and on the microwave signal properties. So first we look at 2x2 spin-Hall nano-oscillators, and we can see that at the smallest separations, we basically only see a single signal. So that's a fully synchronized array at the smallest separations. We can see maybe here at the lowest frequencies that there are individual signals. Same is true when we increase the separation to 140 nanometers. We see some individual signals, but for most of the part, they stay fully synchronized. At 200 nanometers, they stay maybe individual a little longer, and definitely at 300 nanometer separations, there is a wider range of frequencies and currents where we can see individual signals, and only at the highest currents do they fully synchronize. So we can already here in the 2x2 array see that the coupling depends on how far apart the oscillators are. But other than that, they show more or less the same type of non-monotonic behavior. What is slightly different is that the power goes up with width. So you can see here peak power is 14 dB over our noise level for the smallest ones and about 22 dB over for the biggest ones. And that is well known for these constrictions, that the bigger constriction you have, the better signal properties, the bigger power and greater power you have, most likely because the mode volume is larger and less disturbed by thermal energy. Let's now move to the 4x4 arrays. And this is a big step because we're going from 4 oscillators to 16 oscillators. And as we will see, this changes things a bit. So if we go to the smallest separations, we don't see that much difference. Also not at 140 nanometers, but at 200 nanometers, we can clearly see individual signals up until a synchronization event. And if you go to 300 nanometers, there is no such synchronization event at all. Instead, we see 4 very well-defined single signals, but below a certain current, we see even more signals. So what we believe is happening here is that individual oscillators first synchronize in chains. And then, once the chains are acting as 4 individual oscillators, these chains can mutually synchronize together. And we have proven this with Burial light scattering microscopy, that this is indeed what happens. I don't have time to show those images here, but you have to take my word for it that the interactions are more strongly along the current direction than between chains. We can then ask ourselves how far can we go? And we have made 5x5, 6x6, 8x8, and 10x10 oscillators, and I will now show the microwave signal properties of those. So as in the case for 4x4, the 5x5 arrays show a very similar behavior. The largest separations don't yield a fully synchronized behavior, but the smaller separations do. If we increase one more oscillator on both sides, which is 6x6, then we have problems already at 200 nanometers. If we go to 8x8, we also don't synchronize at 140 nanometers. But I want to point out that the power is more or less the same for the 5x5 and 6x6 and 8x8 when they are separated by 100 nanometers. So we have complete synchronization up to 8x8 arrays when they are spaced less, well, they're spaced at 100 nanometers separation. If we go to 10x10, the power drops and there are signs of individual oscillators here. So definitely no complete synchronization for 100 oscillators, but very good and strong synchronization for 64. And we can summarize these signal properties a bit more by looking at their line width and power. So we picked the best line width and the best power from such measurements, and we show them in the next slide. So here we can see that the line width is improving tremendously with n, where n is the number of synchronized oscillators. But I plotted this on a log-log scale because the dependence is exactly inverse proportional to n, which theory also predicts. So the green data are for the smallest constrictions, which are closest together, and you can see that they follow 1 over n dependence all the way up to 64 oscillators. If you make the oscillators larger, they're small. The 2x2 arrays are clearly better if you have smaller, if you have bigger constrictions, and that is we know also from single oscillators. And as long as they stay synchronized, they are better than the smaller oscillators. But it's just the fact that you cannot synchronize them in very large arrays because they don't interact strongly enough. So all in all, the best behavior is for the 8x8 array of the smallest constriction, which has a line width all the way down to 60 kilohertz. And as a function, in terms of quality factor, which is the operating frequency over the line width, we get a number as high as 170,000. And we can compare that to literature values. And here I show a compilation done by Kubota at AIST, and where we can see that prior to our work, which is a star here, the best quality factor was still that by NIST from 2004. But now we are at about an order of magnitude higher than that. So mutual synchronization is indeed a very good way forward to create much better signal coherence in these oscillators. Now, the power of our devices is obviously very low because we use an anisotropic magnetoresistance, whereas we should be using magnetic tunnel junctions, and that's ongoing work that we are currently continuing. Now I want to switch gears a little bit and talk about neuromorphic computing. And I will start with this work by Julie Orlier and Damien Kerlios, where they showed in 2008 how to use 4 magnetic tunnel junction spin torque nano-oscillators to classify spoken vowels. So the network they use is one of 4 neurons. These are the 4 vortex oscillators. They will inject 2 microwave signals through an external antenna. Those are the inputs F, A, and FB. And the output from this network will be how they injection lock, how they respond to these inputs. That would be the injection locking map. And after some optimization, what they could show was an injection locking map of this type, where when they sweep frequency A and frequency B, they get different types of injection locked states from the array. And they could then map the spectral content of spoken vowels onto 2 microwave frequencies, frequency A and frequency B, and show that different vowels showed clustered into well-defined injection-locked state this way. Now, that's an entire talk on its own, and this is just a very, very brief summary of that paper. Instead, I now want to show how we can carry out the same type of recognition using our spin-Hall nano-oscillator arrays. So I will compare our 4x4 array with their 4 oscillators. I will use our 4x4 array in a regime where the chains are synchronized internally, but not with each other. And this gives us 4 neurons, 4 oscillators very closely positioned, very strongly interacting, but not synchronizing. And we will use inputs, but now we will not use an external antenna. Instead, we will simply inject the microwave currents into this array and see how the array responds to these injected currents. There are some slight differences. We have primarily nearest neighbor interaction, whereas the microwave current in Orlier's case leads to a global all-to-all interaction. That does not matter much, as we will see. There are some other important differences. The vortex oscillators operate at some 300 megahertz. We operate at some 10 gigahertz. The MTJ oscillators are individual large oscillators that have their own current control and an external antenna to operate. Our device is about half a micron wide, where everything is done in a single device, basically. So there's some great simplicity here and some potential for actual miniaturization. And when we do the same kind of sweeps of frequency A and frequency B, we find the same type of synchronization map or injection locking map. and the same states are reproduced as in the original work by Julie. Now, to really use these spin-Hall nano-oscillator arrays for this type of work, or for maybe more advanced work, one would like to be able to tune them individually. Remember, for example, that in their original work, they had individual current drivers for each oscillator to be able to tune them. We here relied on the as fabricated behavior and showed that it worked, but to have a general computation, one would like to be able to change these oscillators after production. So what we have done recently is look into how to use voltage control to do exactly that. And one important demonstration was done by Himanshu Fulara last year. Earlier, he had shown that he could generate propagating spin waves in tungsten cobalt iron boron spin-Hall nano-oscillators. Because if you make the cobalt iron boron layer here very thin, you will be able to increase its perpendicular magnetic anisotropy, which eventually will lead to propagating spin waves also in nanoconstriction spin-Hall nano-oscillators. But the PMA has another benefit. It can be voltage controlled. Voltage controlled magnetic anisotropy is a big deal because it allows us to for example, get voltage controlled, voltage programmable MRAM, which is much better than field or current programmable MRAM. And in our case, we can fabricate individual gates on top of individual oscillators and be able to tune their properties without having to change anything in the entire array. And for example, this device here has on top of the cobalt iron boron a set of dielectrics, MgO, aluminum oxide, and silicon nitride, which forms a voltage gate. This particular choice actually shows memoristic behavior, which was not investigated in this paper, but I will show some results later on. First, we'll look at the direct voltage behavior of these gates, of these devices. And what you can see is if you turn on these oscillators, which happens at around 1 milliamp or so, and you tune their frequencies half a gigahertz by 0.5 milliamps, and you then change the gate voltage, you will see that you trace out slightly different frequencies. So if we stay at, for example, 1.2 milliamps, we see that we can change the frequency by 50 megahertz just using the voltage on top of the gate. And that's a sizable change in itself, which can be used to change how oscillators interact and synchronize. What we found, though, in this work, which was kind of surprising, was that the threshold current also changed a lot. So we could change the threshold current by about 20% by applying a negative or a positive voltage on the gate. And that, although I don't have much time to go into the details there, that is because of a giant control of the damping in the constriction. Because when you tune the mode between propagating and localized, you tune the load on the mode substantially, and that leads to a very big difference in threshold current, or in local damping, and hence in threshold current. I then want to wrap up by showing our latest results based on these types of concepts. We have made chains of spin-Hall nano-oscillators with individual gates, and these gates now happen also to be memoristic, so we call them M1 and M2 here. But what I will show is that we can tune the synchronized state through the voltage alone. So this particular plot here first shows at negative voltages on M1, we see that we have one frequency which we call F1, and which we can show belongs to spin-Hall nano-oscillator 3 and 4. They are mutually synchronized together, but they are separate from nanoconstriction 1 and 2, which make up the signal F2. If we now change the voltage on the gate 1, we will tune the top oscillators. The frequency of those oscillators goes down as they approach the frequency of constriction 1 and 2. They start to interact. You can see that the line width deteriorates substantially, and at about 0.5 volt of positive voltage on M1, they decide to mutually synchronize, and after that they stay synchronized. So this is the first demonstration of a voltage gate controlling the mutually synchronized state of a spin Hall nano-oscillator in a chain. And this is work that we did together with the Tokyo University, and it's still under review and been for quite some time, but we are still optimistic that we will get it published. So with that, I finish my talk. I summarize with the following. We have demonstrated mutual synchronization of long chains and two-dimensional arrays. We can see that the signal quality quantified by the quality factor can be now improved by a factor of 10. So an order of magnitude better signal property because we can operate at 60 kilohertz at 10 gigahertz. And I've shown you the potential for neuromorphic computing, and given that we now can voltage control this behavior, we believe that we have great potential to move forward with much more complicated schemes. So with that, I thank you for your attention and wish for a continued excellent conference. Thank you.